Hello and welcome to News About Geology. This is the show for fellow geologists and all you Earth enthusiasts out there. I'm your host, PGO Ricardo Valls. Have you ever just looked at a world map and noticed something kind of funny? How the coast of Africa and South America look like they could just snap together? Well, that simple little observation it sparked an absolute revolution in science. Today, we're digging into the incredible theory of plate tectonics, the mind-blowing idea that the ground we're standing on is always on the move.
I mean, for pretty much all of human history, we just took it for granted that the ground was solid, right? It was fixed. But what if it isn't? What if the continents we call home are actually on a slow, epic journey across the face of our planet?
So, our story really kicks off in the early 1900s, and it starts with the German meteorologist, of all people, who saw something that basically everyone else had just dismissed. He came up with this radical idea. And honestly, it was an idea that got him ridiculed for most of his life.
And this was it. This was Alfred Wegener's big idea. He proposed that way back, maybe 300 million years ago, all the continents we know today were smashed together into one giant supercontinent. He gave it the name Pangaea, which just means all lands. And he theorized that it broke apart, and the pieces have been drifting ever since.
Now, Wegener wasn't just guessing here. He had real evidence. He showed how the coastlines fit. He pointed to fossils of the exact same land animals being found in both Brazil and South Africa. How could that happen? He even showed how ancient mountain ranges and signs of glaciers lined up perfectly across the Atlantic. The evidence was strong, but the scientific community of his day, well, they just weren't having it.
There was one huge, critical flaw in his theory. When people asked him, "Okay, Alfred, what incredible force is powerful enough to push entire continents around?" he didn't really have a good answer. His ideas, like the spin of the Earth, were pretty easily shot down. And without a believable engine to drive this continental drift, his idea was basically shelved for almost half a century.
But then, long after Wegener had passed away, a boom in technology in the mid-20th century let us explore a totally new frontier, the deep, dark ocean floor. And the information that came pouring in would finally give us the mechanism Wegener was looking for, turning his wild idea into one of the most important theories in all of science.
And boy, the breakthroughs came thick and fast. In the 50s, we mapped the ocean floor and found these gigantic underwater mountain ranges, the mid-ocean ridges. At the same time, we discovered that rocks on different continents had different magnetic histories, which proved they had to have moved. And then, in the 60s, a geologist named Harry Hess put it all together and proposed the game-changing idea of seafloor spreading.
The smoking gun was found right there on the ocean floor, and it looked like these bizarre magnetic stripes. See, as new rock oozes up at the mid-ocean ridges, tiny magnetic minerals inside it line up with the Earth's magnetic field. And since that field flips every few 100,000 years, it creates this perfect, symmetrical, zebra-like pattern on both sides of the ridge. It's like a giant tape recording of the seafloor being created and spreading apart for millions of years. It was undeniable proof.
And if that wasn't enough, just look at the earthquakes. When you plot them on a map, something incredible happens. A staggering 90% of all earthquakes on Earth trace a nearly perfect outline around the Pacific Ocean, a path we call the Ring of Fire. This wasn't random chaos. It was the boundary of the gigantic Pacific Plate grinding against its neighbors.
So, with all this evidence suddenly on the table, all the puzzle pieces finally clicked together. That crazy old idea of continental drift grew up and became the powerful, elegant theory of plate tectonics. So let's take a look under the hood.
So this is basically how it works. The Earth's crust isn't one solid shell. It's broken up into these massive, rigid plates that are floating on a hotter, much softer layer of the mantle below. You can almost think of them like giant rafts on a very, very slow-moving river. And it's this constant grinding motion that creates pretty much everything we see, from the deepest ocean trenches to the tallest mountains.
Okay, so what's actually moving these continent-sized plates? Well, it's really a 1-2 punch. You've got ridge push, where new molten rock pushes up at those mid-ocean ridges and kind of shoves the plates apart. But the main event, the real engine of plate tectonics, is a force we call slab pull. As the old, cold, and really dense edge of a plate sinks back down into the mantle, its own incredible weight pulls the rest of the plate along behind it. It's just like a heavy anchor dragging a chain down to the seafloor.
And all the real action happens at the boundaries. Where plates pull apart, we call that a divergent boundary. That's where new crust is born. Where they smash into each other, that's a convergent boundary. And that's where you get massive mountain ranges and volcanoes. And then where they just slide horizontally past each other, you get a transform boundary, like the famous San Andreas Fault, which is known for its powerful earthquakes.
So we've got the evidence, we've got the mechanism. But this stuff isn't just an abstract model. These incredible forces have a direct and profound impact on our world. Now, if you find all this as exciting as I do, from the big theories to what's happening out in the field, I'd personally like to invite you to check out my YouTube channel for even more geology content. You can find it at youtube.com/VallsGeoconsultant/videos.
All right, so why does all of this really matter? Beyond a geology class. It matters because plate tectonics is the master architect of our entire world. It's the reason we have continents and oceans in the first place, and it's responsible for some of the most dramatic and powerful events on Earth.
These plate boundaries are just zones of immense energy. They are where the vast majority of the world's earthquakes, tsunamis, and volcanic eruptions happen. You can think of them as the planet's pressure release valves for all that heat churning away deep inside, creating landscapes of both breathtaking beauty and, at times, incredible danger.
But these violent processes are also a tremendous source of life and resources. That volcanic ash breaks down to create some of the most fertile soils on the planet, which is why people have farmed near volcanoes for centuries. The same heat that drives eruptions also concentrates valuable metals like copper, gold, and silver into the rich mineral deposits that we rely on. And in places like Iceland, we can even tap directly into that geothermal heat for clean energy.
But the influence of plate tectonics goes even deeper than that. It may actually be one of the key reasons that Earth is a living, breathing world and not just another dead rock in space. It's a huge part of what makes our home a Goldilocks planet. Everything is just right for life.
Think of plate tectonics as a giant planetary thermostat. Over millions and millions of years, it has regulated the amount of carbon dioxide in our atmosphere. Volcanoes pump it out, and the sinking of tectonic plates at subduction zones drags it back deep inside the Earth. This huge carbon cycle has kept our planet's climate stable enough for complex life to evolve and thrive, preventing us from freezing over or boiling away.
And if you want to see why that thermostat is so critical, you just have to look next door to our so-called sister planet, Venus. It doesn't have active plate tectonics. Its crust is a stagnant lid, so there's no way to recycle carbon. All the CO2 from its ancient volcanoes just built up and up in the atmosphere, creating a runaway greenhouse effect and a surface hot enough to melt lead. It's a terrifying example of what can go wrong.
And then there's Mars, a world that is tectonically dead. Once its geological engine shut down, its protective magnetic field died with it, and the solar wind just stripped its atmosphere away over time. It's a pretty stark reminder. A planet that can support life needs to be geologically alive at its heart.
So the map that we know so well today, it's really just a single snapshot in geological time. As we speak, the Atlantic Ocean is getting wider, minute by minute, and the Pacific is shrinking. The plates are still moving. So if you ask what the Earth will look like in 200 million years, the only answer is completely different. A new supercontinent might form, new mountain ranges will rise. Our planet isn't a static object. It's a living, breathing world, constantly remaking itself.
And that constant change is maybe the most incredible takeaway of all. The ground beneath our feet is so much more than just rock. It's a story that's being written across eons. Thanks for watching News About Geology. If you want more, don't forget to check out my channel at youtube.com/Valls/Geoconsultant/videos. Stay tuned for more materials to come next.
Welcome to my channel, where you'll find over 2,000 videos on geology, geochemistry, AI, and many other subjects. If you like what you see, help us grow by subscribing, liking, and sharing this channel.
I think these videos are brilliant, and I'm sure you will like them too. Please like, comment, and subscribe, and don't forget to click the notification bell.